Hi, my name is Konstantinos Kasapis. I'm a software engineer at Data Direct Network Storage, and today I'm going to present our work titled Integration of Parallel I/O Library and Flash Native Accelerators and Evaluation of SIONlib with IME. This is a collaboration work with my colleague Jean Thomas Apoaviva and also our partner Sebastian Lurs from Jülich Supercomputing Center. Storage is still undergoing a deep revolution with the arrival of flash devices, storage class memory, and cloud storage. The arrival of such devices brings high level of performance both in terms of bandwidth and latency, but also new opportunities such as the ability to be byte addressable. As a result, software stacks either need to be redesigned explicitly for such devices or highly adapt in order to be able to use these devices and extract their performance. HPC researchers and users have a long and successful history of extracting the best performance from a computing system. However, this comes often at the expense of low-level analysis of the system and careful application optimization. In order to be able to achieve the performance that the storage systems will provide, they will still need to do huge effort and to do huge optimization at their end. I/O libraries have been designed in order to ease this effort, and they provide easier usability and portability between different machines. The goal of this work is twofold. First, to help the application developers to keep their focus at the problem without really requesting in-depth analysis of the storage system, and also to provide to them the performance that the new storage devices offer. The emphasis on the user experience is an important task, and most of the times is really not put in the right direction due to the lack of quantitative metrics. So in order to do that, our solution is based on DDN's Infinity Memory Engine and also the scalable I/O library for parallel task local files, SIONlib. Why do we choose these two technologies? IME is designed to provide user data performance boost, integrating flash storage in the I/O path. SIONlib, on the other hand, is designed to accelerate parallel file system metadata. The combinations of these two technologies is really a perfect match for high I/O performance. The rest of this talk is organized as follows. First, I'm gonna give some background information on these two technologies that we use, IME and SIONlib. Then I'm going to present our evaluation and finally draw conclusions. In the next slides, I'm going to present IME. IME has many characteristics and many features, but for this talk, I'm going to focus only on what is important in order to be able to understand the results that I will present later. IME, in a sense, is a scale-out flash cache layer using NVMe SSDs inserted between the compute cluster and the backend parallel file system. IME is configured as a cluster with multiple NVMe servers. IME handles the I/O data traffic and forwards the metadata request to the parallel file system underneath. The purpose of IME is to accelerate difficult I/O patterns such as small I/O, random I/O, and is also targeting insert files with high concurrency by taking advantages of the flash device characteristics. IME is implemented as a thin software I/O management layer and shifts the burden of complex metadata operation to the underneath parallel file system. So it is a cache and not a file system, and it is important to understand this for the rest of this talk, and this is why we need SIONlib in order to be able to achieve also high metadata performance. IME is usually smaller in size in comparison to the parallel file systems since it consists from expensive NVMe devices. In the next slide, uh, we illustrate the integration of IME in the I/O path. IME has a part that we call IME client, and the IME client is installed in the compute nodes. The IME client is the one that the applications are forwarding the I/O. IME client then aggregates this I/O and sends it to the IME servers. The IME servers on their own will aggregate the user data, they will coalesce it, form large buffers, and then send this large buffer to the parallel file system. Forming these large buffers, we are able to utilize the parallel file system in the best possible way. Another important aspect of IME is that it is log structured. IME is log structured in the IME servers, and also it is log structured in the IME client. In contrast to the parallel and traditional file systems, IME handles writes in a byte addressable manner. For every write request that application will do in an IME system, the IME will generate a so-called fragment. If there are consecutive large blocks, then it will generate many fragments, each of them max size of 128 kbytes. Fragments themselves remove any implicit locking, and thus they are performance agnostic to file sharing. Their log structure is also very good for flash native since it reduces write amplifications on NAND devices. During the read call, frags are visually rendered to know how to reconstruct the data from the fragments. Each fragment, when it is written, it has a timestamp, and in the read phase, we are able to form the latest view of the actual data that had been written. In the next slide, we see how applications are able to use IME. There are several options. One option is to utilize IME using MPI-IO. IME client is already supporting many IME providers without any modification from the users. Another option is to use the so-called IME native client library, that it is a custom API, IO API, that IME offers to the application. Also, they can use the IME Fuse module that we implement a traditional file system and exporting via Fuse. Of course, each of these options comes with advantages and disadvantages. The advantages of having a Fuse to use it over Fuse is that there is no need for an application modification. The advantages of MPI-IO is that there is no need for modification also as in Fuse, but also it utilizes internally the IME native library that is able to export the best performance of the IME system, and using the native client library is also to export the best performance of the IME system, but it requires modification on the user end. In the next slides, I'm going to present SIONlib. SIONlib is a scalable I/O library for parallel access to task local files. There are two major obstacles on parallel file systems that SIONlib tries to solve. The first one is the overhead of metadata operations. on parallel file systems. Metadata operations usually are very costly, and one reason is that there is contention at the metadata server, but also due to the many round trips between the client and the metadata server in order to serve a single metadata operation, file system metadata operation. The other obstacle that SIONlib is designed to solve is the single shared file access that can lead to contention when writing at the same file system block in parallel. So how SIONlib tries to solve these two problems is by providing a task local file view utilizing only a single or a small number of physical files. SIONlib uses a custom SIONlib binary file format. In this file format, it maps logical files into regions of a single file, physical file. Each task maintains the task local file view. SIONlib API can be a replacement for other I/O APIs, for example, POSIX. The open and write calls in this API are collective, and the read and write are independent. This figure illustrates the internal structure of a SIONlib file. The physical file is subdivided into sequences of blocks, which themselves contain one chunk of data belonging to every logical file. The chunk size can be specified upfront when we open the file. If we don't know the amount of data that each task will write, then we can just don't specify the size and SIONlib will select a sensible default. In case the amount of data that each task writes exceeds the size of the chunk assigned, a new chunk will be allocated and be used by this task. SIONlib itself transparently handles the movement between the chunks that are allocated per task, so the user doesn't have to worry about that. The chunks are aligned in file system block sizes, therefore there is never a contention between tasks that are writing in the same file system block. Having provided sufficient background information, I will continue this talk presenting the evaluation. As I said in the background slide for IME, IME can be utilized in several ways from the client, and one of those was the IME native, that is a custom API, I/O API that IME offers to application. It is very similar to POSIX. For this work, what we did is that we integrated this custom API into SIONlib. SIONlib itself has 3 layers that forward the I/O request from the application to the actually supported interfaces. It already supported RCC and POSIX I/O, and with our addition, it now supports also IME native. When the users, the applications, open a SIONlib file, they can specify which interface they would like to use as a low-level interface. The user might also not specify a low-level interface at all, but internally we can identify when a file resides in an IME server, and then we will automatically open it with the IME native. In the next slide, we illustrate our evaluation methodology. We leverage PARTEST, that it is a benchmark provided as part of SIONlib that can exercise different I/O patterns. The parameters of PARTEST that we exploit are the following. First of all, we can specify the file per process. Then we can specify if we need a single or multiple files. We can modify the chunk size and the buffer size. And of course, we can select the low-level interface that we would like to utilize. Either POSIX, either the IME native are the ones that we select. And then we have three different use cases that we explore. The first use case is using the parallel file system. In that case, it is the Spectrum Scaler version 4, that it is formerly known as GPFS, without the use of IME. Then the other one is IME, using the IME fuse. And last, we evaluate the IME performance using the IME native interface. As for the testbed where we run our experiments, we use the Jülich supercomputing center, and we run all the experiments in Joule's cluster. There is an IME installation there that consists of 54 IME servers that are configured with up to 2 IME server node failures and 9+1 parity encoding for storage device failure. So these two numbers are quite important, since it requires a bit more work than what the parallel file system do. The compute nodes are dual socket Intel CPUs with two 24 cores and 96 gigabytes of RAM, and InfiniBand EDR Connect X4, allowing up to 12.5 gigabyte per second network transfer. For all the experiments, we write a file of 128 gigabyte per node, that it is sufficient to fill the caches and also provides stable results across multiple runs. While we are running the tests, the system is also being used by other users, since it is in production, but we see that there is not such a huge discrepancy from this. The first result that I'm going to present is scaling with a number of processes. This figure presents the aggregated write throughput reported by partest, varying the number of processes, strong scaling, from 1 to 48, that corresponds to the number of cores on a single Joules node. For this scenario, we utilize a single node, and we operate in a single shared file, that it is the SION format, with a chunk size of 2 gigabytes and a buffer size of 1 megabyte. Both the chunk size and buffer size have been selected to deliver the highest throughput among all use cases. In the x-axis, we have the number of processes, and in the y-axis, we have the aggregate write throughput in megabytes per second, and of course, higher is better. As we can see, with a single process, IME native offers about 18% faster than IME fuse, and it's about 40% faster than GPFS. I will call GPFS Spectrum Scaler from now and on. I think it's easier for me. GPFS is able to achieve the maximum performance of around 5 gigabytes per second with 16 processes. For IME native, the best performance is achieved with 12 processes, and it is around 9.1 gigabytes per second, that it is only 30% less than the theoretical maximum that the network interface offers. Remember that I said on the configuration of the IME system that we have also node fault tolerance, IME server node fault tolerance and also device fault tolerance in the server side. So this number accounts also for the overhead of these two things. What we also observe from this figure is that the IME fuse performance is not really improving, and it's actually decreasing as we increase the number of processes. So this is due to a lock that the fuse library has internally and does not allow parallel writes in a single file. In the next set of tests, we explore the scalability varying the number of nodes used, the so-called weak scaling. We maintain the same amount of data written per node as in the previous experiments. For this experiment, the number of processes used is 16, that it is the number that was delivering the best performance for GPFS. As in the previous figure, in the y-axis we have the aggregated write throughput, but now in the x-axis we have the number of nodes used. We see that IME native performance scales linearly with the number of nodes used, doubling every time we double the number of nodes, reaching 71 gigabytes per second with 8 nodes. And this is only 30% less than the theoretical maximum, and we have similar as in a single node. It continues to deliver faster throughput with 16 nodes by a factor of 1.35 in comparison with 8 nodes. GPFS performance also improves when we move from 1 to 2 nodes by a factor of 1.48. But the trend does not continue when we move to 4, that only improves of around 20%. It reaches the maximum performance of 17 gigabytes per second with 8 nodes, and the performance drops back to 16.6 gigabytes when we double the number of nodes. IME fuse also improved by around a factor of 1.7 when we double the number of nodes, but again, the performance of IME is very limited due to IME fuse is very limited due to the issue we have with the fuse library that does not allow writes in parallel in a single file. In the previous slides, we saw that there is a substantial difference between the performance of IME fuse and IME native. Apart from the actual lock that prevents parallel writes in a single file from the fuse library, there is also additional overhead. In this slide, we illustrate the I/O path from the application to the IME client and back using the IME fuse and IME native. As we can see, when you use the IME fuse, we have to cross the kernel 2 times, where with the IME native, there are direct calls from the application to the IME native and to the IME client. Let's now see in terms of numbers how this difference translates. In this experiment, we modify par test in order to use a single file per process. In the x-axis, we have the number of files and the number of processes used, and in the y-axis, we have the aggregate write throughput in megabytes. As we can see, the performance of IME fuse now increases with the number of processes used, since now each process has its own file. However, there is always some difference in comparison to the IME native, and we can see that as we use more processes, then this difference becomes more apparent. Next, we perform some experiments to see the performance effect of the two parameters of SIONlib. The first parameter is the buffer size that defines the amount of data written in each I/O call in the SIONlib. To evaluate this, we run tests varying the size from 4 kilobytes to 1 megabyte. All these tests are executed in a single node with 16 processes sharing a single file, and we have a constant stack size of 2 gigabytes. The results are aggregated write throughput, and this is in the y-axis, where in the x-axis we have the buffer size in kilobyte. From the figure, it's apparent that IME performance is not really impacted by the buffer size, where GPFS needs at least 64 kilobytes as a buffer size in order to perform the 5 gigabytes per second that it is the maximum it can get. In this slide, we demonstrate the performance impact of the chunk size. The configuration of this experiment is the same as in the one above, but in this case now we modify the chunk size from 16 megabytes to 1 gigabyte, and we keep constant the buffer size of 64 kilobytes. That was the number, as we saw in the previous one, that GPFS performed its maximum. Similar to the previous experiment, the chunk size does not impact IME performance, where it greatly impacts the GPFS performance. Needed at least 128 megabytes in order to start achieving its maximum performance. With that, we will conclude our evaluation, and we will move to the conclusion section of the presentation. So what we saw today was that the integration of IME and SIONlib outperformed traditional parallel file systems by far, but it was something that was expected, right? So we integrated flash storage in the application's I/O path. The good thing is that we showcase that such integration really is benefiting in terms of performance, but we also did that seamlessly in regards to the application developers, since there was really no code modification needed to the benchmark that we used. And with that, I would like to finish my presentation, and thank you. Of course, you can send me an email for any questions that you have.